How fast can I windsurf? What does physics say? How can we determine the sailing speed when windsurfing, and what are the physical limits? As already mentioned, the maximum sail force results from the moment equilibrium of rider weight and sail force, as shown in the picture. The weight moment with rider weight G body, with the lever arm D, and the sail moment with the sail force F and the lever arm H. The sail force F is then G body times D divided by H. The sailing speed results from the equilibrium condition sum of all acting forces equals 0, as shown in the figure. These are the forces in the direction of travel, the thrust T and the water resistance or drag D of the board, and the sail side force transverse to the direction of travel and the side force of the board and fin. There is a course direction in which the speed is greatest in a given wind. This course is called the optimum course for speed sailing. As shown in the picture of the wind triangle, this is the course at which the angle between the true wind Vt and the apparent wind Va is exactly 90 degrees, or right angle. The speed Vs is the vectorial sum of the other two speeds. For this condition, the heading is equal to 90 degrees plus the apparent wind angle gamma A. For this condition, the thrust is maximum. The speed reached cannot be determined from the speed triangle. It depends only on the magnitude of the applied forces. Since we have a right-angled triangle, we can easily determine the apparent wind angle gamma A. The angle function for the sine shows that it is equal to the ratio of the true wind Vt to the speed Vs. In other words, the reciprocal value is equal to the ratio Vs to Vt, which is usually used as the ratio to show how much faster a vehicle is sailing compared to the wind speed, for instance 2 times faster than the wind. If Vs to Vt is large, the apparent wind angle is small and vice versa. The determination of the sailing speed can be calculated from the forces applied. The speed is reached when the thrust T is equal to the drag D. The thrust is equal to the sail force F times sin of gamma A, also F times Vt/Vs. The following then applies: the drag changes with the square of the speed according to the law of drag. Drag is equal to half the value of the water density ρ times the speed Vs squared times the reference area F and times the drag coefficient Cd. The point of intersection provides the speed. The graph clearly shows that the thrust decreases with 1 through Vs, while the drag increases squarely. The speed can only be increased if either the drag decreases or the thrust increases. The only way to increase the thrust is to increase the wind, as the sail force is limited by the body weight. If we solve the equation according to Vs by Vt, we see that the ratio of the speeds of speed to wind is equal to the ratio of the sail force to the hydrodynamic drag. Since both the sail force and the drag are speed dependent, it is not possible to determine the sailing speed directly. A solution results from the fact that the sail force is determined from the moment equilibrium via the body weight, and further it is known that the drag changes quadratically with the speed. If we use the body weight for the sail force F from the moment equilibrium, the result is, or, resolved according to Vs. This makes it possible to calculate the sailing speed directly. It results from the third root of the body weight times the lever arm ratio to the drag area and multiplied by the wind speed. This means that every change in the constant values or the wind speed changes the sailing speed with the third root. This equation applies to all sailing vehicles. In contrast to the windsurfing board, the body weight is replaced by the total weight or by the special counterweight. If we summarize the constant values as a factor A, then we can write Vs is equal to the third root of factor A times Vt. The graphical representation of travel speed versus wind speed shows the curve shown in the figure. The constant factor A represents the rider's weight and the design features of the board. The riding speed then only depends on the wind speed. The constant A can be easily determined from a test run by dividing the ridden speed to the power of 3 by the wind speed. This extracted factor A is the personal performance value, contains the personal weight, the characteristics of the windsurfing system, sail, drag, and the environmental conditions with regard to course, wind force, and surface smoothness of the water. We can use this value to determine the sailing speed at a different wind speed under the same external conditions. Furthermore, we can easily calculate what effect a change in the factor A has on the sailing speed with the same wind. An increase of factor A by, for instance, 20%, which corresponds to either an increase in weight or a reduction in drag or both, would increase the speed by a factor of third root of the change factor. By increasing the factor by 20% would correspond to a 6.26% higher speed. If we use Antoine Albo's data with the world record speed of 53.27 knots as a reference, the maximum speed would increase to 56.6 knots. The course of the sailing speed over the wind speed would be as shown in the figure. An improvement of the value of by 20% is very unrealistic. As the weight of the rider can only be increased insignificantly, the hydrodynamical drag would practically have to be reduced by 20%. Conclusion: the maximum speed with a windsurfing board has been reached. The reason for this lies in the limitation of the sailing power by the maximum possible body weight. An increase in speed is practically only possible with even higher wind forces. Heavy and tall riders always have an advantage. It is striking that practically only standard material is used in the world record attempts. There are no elaborate special constructions or sails, boards or fins specially developed for the attempts. The Horonuku and Sail Rocket 2 case are quite different. Here, an immense amount of time and money was invested. The Sail Rocket 2 took 10 years to develop. The new developments SP-80 and Sirocco are also being developed at an extremely high cost. The SP-80 project has already been running for 4 years. Only other designs, which are no longer windsurfing systems, have to be used to break the world record. One possible solution for a kiteboard could be, as in the Sail Rocket project, to move the kite's point of attack to the surface of the board and also to arrange the fin in such a way that the kite force is precisely compensated. The rider receives a residual force via a connection to the kite so that he is able to control the board and the kite. This allows the kite size to be enlarged and the sailing power and thrust to be significantly increased.